Now, okay, we're in the home stretch. Let's finish this stuff up. Okay, let's finish this stuff up. Here we go. You can imagine that each one of these has a very, very complicated equation that goes along with it. There's an equation that tells you exactly how much length will shrink, and there's an equation that tells you exactly how much time will slow down depending on how fast something moves past you. But if you combine the equations of special relativity together, a lot of the hard parts of the equations cancel out, and you're left with a much simpler equation, which you can see right here. Here we go. Boom. Yes or no? Have you ever seen this equation before? Have you seen this equation before? Yes or no? Yeah. I mean, they throw this in cartoons all the time when they want to show a smart person. Now, this right here is only true because these crazy things are true. But this is much easier to understand. Let's go through it real quick. Do you guys know what the E stands for? What's this E probably stand for? We've actually seen the capital E in other equations. What's that E stand for? Nobody wants to try. That's okay. That E. Oh, here we go. We get some try. We're getting some tries. Well, it stands for a word that starts with E. It's energy. And light is a type of energy, but it's energy. E is for energy. Okay, just like in an old equation we had like a few weeks ago. Okay, so E is energy. What's the M probably stand for that we talk about all the time? What's that M stand for? I think you guys will get this one. What's that M stand for? Mass. Mass. Yeah, that's mass. Now this C, that's the speed of light. Okay? C is the speed of light. So E equals mc squared is saying energy equals mass times the speed of light squared. Okay? And what this is getting at is something you may have learned in school. Okay? You may have learned in school. Can you create or destroy matter? Can you create or destroy matter? Let me ask you that. Can you create or destroy matter? Can you create matter out of thin air? You probably learned in school that you can't. That you can't create matter, you can't destroy matter. But it turns out Einstein figured out 100 years ago that that is not true. What this equation is saying is that you can destroy matter and you can create matter. But according to this equal sign, if you want to create matter, you have to make it out of energy. And if you destroy matter, what do you get? What does it turn into? Let's see if you can guess that. If you want to create matter, you got to make it out of energy. But if you destroy matter, what are you going to get? What are you going to get if you destroy matter? So to create matter, you needed to use energy. Yeah. So if you destroy matter, you get energy. So putting all that together, what this really means is that energy and matter are two versions of the same thing. Matter can be turned into energy, and energy can be turned into matter. Okay? Now, this right here is why the sun shines. Okay? Remember, when we talked about how the sun shines in one of the previous videos, we said it was because of fusion, right? Because of fusion. And specifically, our sun right now fuses 4 hydrogen atoms together to make a helium atom. Now, don't overthink this. If we were to take 4 hydrogen atoms and weigh them, we put them on a scale, and then we fuse them, we stick them together, and put them right back on the same scale, it seems like they would weigh the exact same thing. They would have the same mass. 4 hydrogens, stick them together, make a helium, put them back down. Seems like it would have the same mass. But it turns out that when you do that, when you fuse hydrogen atoms, stick them together, and set them back down, you'll always have a little bit less mass. You'll always have a little bit less mass. Whenever you fuse hydrogens, the result always has a little bit less mass. So that means what's happened to a little bit of the mass? If we take those hydrogens and put them together, a little bit of the mass gets destroyed. But what does that little bit of missing mass turn into? What does that little bit of missing mass turn into in this case? I'm asking you guys that one. What is that? If we fuse hydrogens, we lose a little bit of mass in the process. What does that little bit of mass turn into? According to what I've been saying here. Yeah, it turns into energy. And what kind of energy? Well, remember we said that fusion creates light. Light is a kind of energy. So the whole reason that fusion creates light is because a little bit of mass gets destroyed and it turns into energy. So E equals mc squared is why the sun can shine. So we would be dead if E did not equal mc squared because we need that light. Okay? And remember though, this that we rely on to be alive is a result of all the crazy stuff that we talked about up there. Here's the very last thing I have to say about this. C squared. Is C squared a big number or a little number? Is C squared a big number or a little number? Remember, c is the speed of light. So if we take the speed of light and square it, it's going to be a very big number. So what does this mean? Check this out. If we look in the equation, if c squared is a very big number, if we destroy some mass, this equation tells us how much energy we get. If we destroy even a little bit of mass, if we multiply that by c squared, am I going to get a lot of energy or a little bit of energy out of this process? When I destroy some mass, even a little bit of mass, am I going to get a lot of energy or a little bit of energy? A lot. You get a lot of energy, even out of a tiny bit of mass. This produces a ridiculous amount of energy. Even if I plugged in a small number here, because c squared is so big, I'm going to get a lot of energy, even out of destroying a little bit of mass. But that also means if I want to create some mass, I need a lot of energy to do it. So a little bit of mass means a lot of energy. Now, there was a very, very, very dramatic proof of E equals mc squared in Einstein's lifetime, a time where we destroyed a tiny bit of mass and created a ridiculous amount of energy. Does anybody know what I'm talking about? Does anybody know of the very dramatic proof of E equals mc squared that happened in the 1940s? Here's a little bit of a hint. Towards the end of World War II. What am I talking about? Oh, you guys got to know this. That's okay. I'm talking about. Oh, somebody's giving it a try. There you go. You got it. I'm talking about nuclear bombs. The reason nuclear bombs are so destructive is because of E equals mc squared. In a nuclear bomb, we're destroying a small amount of matter inside the bomb. and that produces clearly a ridiculous amount of energy. It's an unfortunate side effect of learning a new thing, is that human beings always end up using it for some destructive purpose. On the other hand, this is also what we use in nuclear power plants. In nuclear power plants, a little bit of mass is destroyed, and we produce a lot of energy there. So bad things and good things have come from this. But we need that to be alive, because that's why the sun shines. All right, that's all we're going to say for today. When we come back next time, we're going to talk about general relativity and put all of this in place for the black hole. So more craziness next time. I know today was very, very confusing, but I'll go ahead and reassure you, I am not going to ask extremely complicated questions about this on the test. I'm going to try to ask very basic comprehension type questions for this stuff. Let me give you an example right now. Here's an example right now. Here we go. Let's say somebody runs past you. Let's say someone runs past you. What do you see happen to their length? What happens to their length from your point of view? Let's put it all together. You see someone run past you. What do you see happen to their length? It gets... Yep, here we go. Shorter. It shrinks a little bit. But from their point of view, here we go, last question of the day. From their point of view, what would they see happen to your length? Assuming they could see these microscopic changes. What would they see happen to your length as they ran past you? You would also shrink. Okay, so I'm only going to ask basic questions like that. Oh, and when I ask these questions, when I say, what does this person see? Let's always assume on all questions that even if the difference in speed is not very much, that all of the people viewing can see microscopic changes. Let's assume that for all test questions.